Started. So we're very pleased to have got Kravitz from UT Austin here to talk to us today. So Scott did his PhD at Stanford University, working on XO 200 with Giorgio Grata and Dave and Mike, actually, before he went to LDNL for his postdoc, where he worked on LZ. Right. Yep. And now he's recently become a faculty member at UT Austin, where he's continuing to work on LZ and also do some interesting things like crystal xenon. So please take it away.
Great, thanks, Tom. So yeah, LZ is my day job. This is sort of the fun R&D project I do. It's a lot more interesting to talk about personally. So I'll tell you why I think solid xenon is an interesting and compelling idea for use in particle physics. So brief outline of the talk today. I'm going to tell you a little bit about LZ's search for dark matter. And tell you why radon is a problem for these xenon TPCs in particle physics. I'm going to tell you how you can use crystal xenon to deal with that problem of radon backgrounds. I'm going to hopefully convince you that it's not crazy to use crystal xenon for particle detection based on some sub-kilogram scale tests we've done at LBNL that sort of demonstrate you can use this technology equally well as the liquid xenon TPC, which is already well established. And I'll talk about plans for exploring this crystal xenon technology and really making it feasible to do at the 100 kilogram to ton scale that you really need for most of these applications. Okay, so for those of you who aren't familiar with the LZ experiment, it's a primarily a dark matter search. It consists of 3 detectors. The innermost is the time projection chamber, which contains 7 tons of active xenon volume. So it's quite large. You can fit inside of it. I have personally been inside of it, doing some tiling of some plastic in there. In addition to the main TPC, I'll explain how the TPC works in just a minute if you're not familiar. There's also a liquid xenon skin veto. So there's a region just outside of the TPC that's instrumented for vetoing backgrounds. And outside of it, there's an outer detector, gadolinium-loaded liquid scintillator, which is also a veto system. So this whole experiment is located almost a mile deep in the SURF research facility in Leeds, South Dakota. So let me explain the basic technology of the xenon TPC. So if you have a particle coming in, this could be a dark matter particle like a WIMP, or it could be a background like a gamma ray. If it scatters off of a xenon atom in the detector, that energy going into the xenon shows up in basically 2 channels, light and charge. So the first thing this xenon does is it scintillates. The chemical process, it emits light isotropically, and we detect that with very sensitive light detectors, photomultiplier tubes, at the top and bottom of our TPC. Those are these little cylinders here. And in addition to that S1 light, we get ionization. Some of the electrons get stripped from their atoms. We set up an electric field in the detector, and that drifts those electrons from their initial interaction position to the top of the detector. Now, in a detector like LZ, this is what's called a dual phase time projection chamber. So this tank of xenon is not completely full. When the electrons reach the top, they transition from the liquid phase to the vapor phase. They get extracted into the vapor, and there they accelerate and create an avalanche of secondary electrons, which also creates, as a byproduct, xenon scintillation light. So that avalanche creates what we call the S2 signal, the second light signal, which we detect primarily with our top array, but also the bottom array. And so we get to measure the total initial scintillation response and indirectly the ionization signal through this S2. Because that S2 is focused in the top array, it's highly localized. We can use the hit pattern of those PMTs to infer the XY position, the position in the plane of the PMTs. So in this example, it's somewhere near where the red PMT is. And then we can use the time between the 2 signals, S1 and S2, to infer how long it took the electrons to drift. And we can translate that into a depth in the detector. So we get full 3D position reconstruction, in addition to the size of the S1 and the S2 signal. In an experiment like NEXO, you can use the light and charge signals in a weighted way to get an energy, reconstructed energy. We are not typically so interested in energy. We look at actually the two-dimensional space of the S2 signal and S1 signal. And the reason for that is that the ratio between the two is very useful for distinguishing between electron recoils and nuclear recoils. So our typical backgrounds in LZ, these are external gamma rays or internal beta decays that impart their energy to the electrons surrounding the xenon atom rather than the xenon nucleus. Whereas a WIMP interaction would interact by scattering off of the nucleus of the atom. That's also true for neutron interactions, and some neutrino interactions will be nuclear recoils as well. So we can very efficiently discriminate between our primary background, which are electron recoils, and our potential signal, which is a nuclear recoil, using this ratio, the S1 to S2 light. Give people a chance to ask questions if they're not familiar with this.
I'm just curious about what the sort of time between S1 and S2 is. Do you run into issues with after pulsing from the PMTs, like covering this up?
The typical delay is on the order of 100 to 1,000 microseconds. So after pulsing does happen in our PMTs, it adds essentially some extra noise that we have to calibrate out, but it's ultimately not really a dominant factor. The question. Okay, I'll move on. So I'm going to jump straight ahead to the first results of LZ, since this isn't an LZ talk. So our first data set started in December of 2021 and ended in May of 2022. So it's a relatively short time period. And with that first data set, about 60 days, we found no evidence of WIMPs at any mass. So we did the thing that all self-respecting dark matter experiments do when they don't see anything, which is we told everyone how good we were at almost seeing dark matter or trying to search for dark matter. The way we quantify that is typically in this two-dimensional space. The y-axis is the WIMP nucleon cross-section. So this is a parameter that governs the strength of the interaction between WIMPs and a nucleon like a proton or a neutron. Larger is a stronger interaction, and our interaction will also depend on the mass of the dark matter particle. So essentially the way to interpret this black line, which is our ultimate limit, is that any points above that black line correspond to stronger WIMP nucleon interactions than essentially what we can exclude at 90% confidence. So this region of parameter space up here is now strongly disfavored by the LZ experiment. And you can see if we compare this to other world-leading experiments, we're currently the best at searching for these WIMP dark matter models in this wide range of masses. And to quantify that more, we did almost 2 times better than at high mass than the next best experiment, which is Panda X in China, and about 3 times better at intermediate mass, where the next best experiment is not shown on the plot here, but it's xenon n-ton, which is a very similar technology. Their paper came out after ours, which is why the plot isn't on there, but you can look it up when we get there. So it's really exciting, even though we didn't find dark matter, because we were able to be world leading across 3 orders of magnitude in WIMP mass with only 60 days of data. And we're going to keep running the experiment for several years. So we expect a significant improvement in our data in the next 4 or 5 years or so.
Sorry, can I have a quick?
Yeah.
So it looks like you cut your limit. It was actually stronger than you reported, 20
Correct.
mg. So you think that's just a background under fluctuation? I mean,
Yes. So at low energies in our parameter space, low S1s, we happen to get a deficit of events, and it happens that these WIMP models, they tend to be sort of quasi-exponential. So you get, particularly at lower masses, they're focused near those lower energies. So we get an enhancement there based on the fact that we happen to be lucky. We got a background under fluctuation. So without any extra constraints, the dashed gray line is what we would get. And we just do what's called a power constraint at the 1 sigma level. Basically, we say we probably shouldn't exclude these models because we kind of happened to get lucky.
But it looks okay in the sidebands, it's just in the WIMP search region that it looks low, is that right?
It's only in, it's not even in the full WIMP search region. It's really a relatively small, between you and me, Dave.
Yeah, we can take it.
The new, no, I can tell you, just don't tell anyone else in the room. The new data doesn't seem to show that.
Okay.
Yeah, we think it's really statistical fluctuations. Okay, so let's talk about the future of direct detection. So WIMPs remain really strongly motivated. There's still lots of really interesting theories that end up in this flavor of dark matter model called the WIMP. For example, Higgs multiplets are things that are sort of beyond what we can search for in these first data sets. In the next several years of LZ's running, we expect to be able to continue to probe these important theory benchmarks. But if we don't see anything, then even by the end of LZ's running, then there's still really strong motivation to continue searching for dark matter. Essentially, this is one paper that shows some of these electroweak multiplets. The predicted masses and cross sections are sort of shown by the blue and red points. And the corresponding cross section that you'd need to reach for those is further than where we are now, further than where we even expect to be at the end of LZ's data taking. So there's a good motivation to continue these experiments down to as far as we can take them, hopefully to find dark matter, but if not, to say we tried really as hard as we could and we really couldn't find anything. And the thing that will ultimately limit this xenon type dark matter experiment is what's called the neutrino fog, or sometimes called the neutrino floor. This is the point where astrophysical neutrinos, they do cause nuclear recoils and therefore are very hard to distinguish from dark matter. So this is the point where you become background limited by astrophysical neutrinos. I want to take a moment to pause and contemplate how exciting it would be to have a detector where you've gotten rid of all of the backgrounds except for neutrinos, which are notoriously hard to detect in the first place. So it's where we want to be. It's really hard to get there. We're more than, by the time LZ is done, assuming everything goes well and we reach this sensitivity, we'll still be more than an order of magnitude away from this neutrino fog. So some people might say that's just around the corner, but realistically, we're talking probably a decade or more, maybe a couple of decades before we get there. So the question is, if we want to keep going beyond LZ, what's limiting us? And one obvious answer is just raw exposure. You want a bigger detector. You want more mass. You want to run longer. That, of course, can get you there faster. But you won't get there very effectively if you haven't removed those other backgrounds besides neutrinos. And in fact, right now, we are not in a state where the experiment is limited by neutrinos. It's limited by the dominant background, which is radon. I'll talk about what I mean by that more in just a second. There's also a question of these existing experiments are already kind of reaching some engineering challenges with the way that they're produced. And I think the core challenge that makes people really nervous is achieving the high voltages needed for setting up these electric fields. And in particular, for the dual phase TPC, setting up the really strong electric field you need in the extraction region, where you go from the liquid to the gas. So can we go to a bigger detector? Yes. How painful is it going to be? I don't know. Okay, so let me explain what I mean when I say that radons are the limiting background. So this plot here shows the LZ data from the first 60 days of data. So this is in our typical analysis space of S2 versus S1. The black points are our data. The gray bands are our overall background model expectations, 1 and 2 sigma. And the red dashed line is what we call the nuclear recoil band. It's that region of lower S2 to S1 ratio where we expect nuclear recoils on average to occur. And we do have leakage of events into the nuclear recoil band, but that's consistent with pure background. So in this initial data set, we have something like 330 events. A decent fraction of those come from xenon 127 and argon 37, which are short-lived. So they're now already out of LZ. The remaining primary backgrounds are lead-214 and lead-212 beta decays, which are part of the radon chain backgrounds. So what this means is that there is essentially this radioactive gas radon that's being emanated from detector components. That's the cryostat, that's the plastics in the detector, that's our PMTs. It's continuously being put into the detector and it's decaying down the chain, and the lead are the problematic decays. The reason for that is that alpha decays are really high energy, they're monoenergetic, they're easy to say that's not dark matter. The beta decays, they're a continuum. So they could take any energy, they could be at the low energy that most of the dark matter models are interested in are at. And by chance, some of them do happen to fluctuate into our nuclear recoil band. Okay, so if we got rid of that, as well as krypton, which we can distill out, then our next dominant background is really neutrino interactions. So sort of a roadmap for getting to the neutrino fog is remove the radon. We also have to remove the krypton. Krypton's way easier. Ask me about it if you want. So what is the impact of removing radon from the detector? So just visually, here are some projections of LZ data several years down the line. I think this is 1,000 days of data. On the left, with radon, and on the right, sort of a homebrewed version of this where the radon has been removed. And we've injected a fun little signal of 3 dark matter events here. And you can imagine trying to say you detected new physics against a background that looks like this. It's going to be a hard argument to make. Whereas here, these 3 data points look kind of compelling. So just visually, you can tell the difference between how clean of a search for new physics it is, particularly new physics of some flavor that we might not be expecting when we've removed the radon. In terms of how we quantify the sensitivity, something like an LZ experiment could reach the neutrino fog at high masses about 3 times faster if we're able to remove the radon. I'll talk later in this talk about other potential things you can do with detectors that don't have radon. Yeah.
What backgrounds do you have now linking into this signal band there? What
Yeah,
does it respond to? Oh, on the right, without radon, sorry.
which ones are these going to correspond to? Off the top of my head, I don't remember what those would be most likely to be. I don't know. I have to look at that.
Okay.
Okay, so if the problem is radon, can't we just remove the radon? Can we purify the xenon to remove it? This is something that people are working on. I would say the xenon Inton collaboration has done the best at it so far, but it's incredibly hard to really get the radon to the level of, you know, a handful of atoms that we really needed to get to. So essentially in these experiments, you're continuously circulating your xenon to chemically purify it. There are approaches where you can, generally that doesn't work for radon because it's a noble element. So the chemical purification doesn't do anything. So you need to remove it with something like, there's a charcoal chromatography approach, or you could remove it through distillation. Those are, I think, the only 2 methods I've really seen that work. And both of them basically are incredibly challenging to do at the scale you need to reduce the radon by a huge amount. So Xenon Inton has gone through a really heroic effort, and they've been able to reduce their radon by a factor of 2 with enormous circulation rates, 200 SLPM. It takes a lot of power to run a distillation column that can do this. So if you imagine scaling this up to a 10 times bigger detector, it's going to be really challenging. And I think the key thing here is that this approach of removing the radon through purification is fundamentally limited because the radon is continually being emitted into the xenon by the detector components. So you need that radon to flow out, get purified, and return for this to be effective. So your turnover time of the xenon mass has to be comparable to whatever fraction of that radon decay time that you want to remove. So if you want to remove 100 times 99% of the radon, you need to circulate, something like 100 times per lifetime of the radon, which is 4 days. So that's a big ask. So finally get to the crystal xenon part of the talk. The proposed solution here is to prevent the radon from being emanated into the detector at all by turning it into a crystal, by solidifying it. So if you freeze it, now the radon at the edges of the detector being emanated is not going to diffuse in any significant amount through the crystal. So you exclude new radon from entering the bulk of the material, and the radon that was left over before you do the freezing, that decays away relatively quickly. So we've got a plot over here that shows the radon rate in terms of 3 of its daughters as a function of time. The radon decays away quickly with this 4-day half-life. So after 100 days, it's completely negligible. You get some longer-lived daughters coming in later, but they're at a much lower level. In addition, these daughters are things that you can actually tag and veto, because each decay along the chain will remain at the same position in the detector once it's crystallized. I'll talk about that in a second. So you end up getting a reduction of these radon chain daughters by something like a factor of 100, and that ends up making them radon now completely subdominant to neutrino. Okay, so here's the idea of this radon tagging approach. This is sort of the second order effect to the dominant thing, which is just excluding the radon from the first place. So here is the decays of the radon 222 chain. We've got radon, polonium, lead, bismuth, polonium, and a traditional liquid xenon time projection chamber. At each step along the decay, these daughters have moved a significant amount because of convection in the liquid. In the crystal, we expect them to remain at a fixed position. So our primary culprit that we want to remove, this lead 214 beta that's very hard to tag, we can now veto it based off of the much easier to tag polonium 218 alpha, or the even more distinguishable bipo decay, where you get a beta decay followed by, within a few hundred microseconds, a nice big alpha. So the way this would work is if you see one of these bipo decays at a given position and time in your detector, you go back a few times this 20-minute half-life, and you say anything from that position in the detector, you remove, and the entire rest of the volume is okay. So it's a very efficient veto. Whereas if you have to say, use the entire volume of the detector or a much larger volume as you do in liquid xenon, you end up having to veto a very large fraction. You lose a big fraction of your lifetime. I want to highlight that this idea of radon tagging in solid is not a new idea. This is something that the DOMIC collaboration has used in the silicon substrate. Yes.
So I'd say it's similar for the radon 220.
Yes.
So you're also looking at the bipo beta alpha decay.
Yeah.
Do you have enough time resolution for to resolve the second alpha decay? Because that's like 7 microsecond half-life, I think.
Yeah, I think you do have enough resolution, just barely. But if not, I think you could probably do just by the size of the alpha, you could probably figure it out. But The radon 220 background is much, much lower. If we look at this here, in this case, it's the lead 212 that corresponds to that, I think, and it's an order of magnitude lower. So it would be more challenging in that chain, but it's also less important. Okay. So crystal xenon maybe gets rid of or does get rid of the radon problem. Can you actually use it in a practical particle detector? The answer is yes, we've done it. I worked at LBNL basically establishing this proof of principle that you can do a two-phase crystal to vapor time projection chamber at a small scale. So the schematic of this detector is shown on the right. We have our usual TPC arrangement where there are some electrodes called the cathode, gate, and anode. And there's a phase change between the gate and anode between either liquid or crystal and vapor. We do our detection in this case, not with BMTs, but with silicon photomultipliers, which are much more compact. And we do our cryogenics by, we have a cold head connected to a cryocooler that cools down our detector at the top and bottom through copper thermal lengths. So we essentially can set a gradient between the top and bottom of the detector and do temperature control that way. So this particular experiment is quite small, 700 grams of xenon, but we're able to establish that it works. A little bit more about the cryogenics and operation here. So a question I often get when talking about this is how hard is it to freeze xenon? And it's very easy to freeze xenon. It's 10 to 20 degrees colder than liquid xenon operation. So if you have a detector that's already able to liquefy the detector, you probably have the cryogenics capable of freezing it. The key challenge is not can you get solid, but can you actually grow a good quality crystal that's transparent, that has all the particle properties that you know and love from the liquid xenon version of this. And to be clear, we're not talking about really single crystal growth. I think these are probably polycrystalline structures, but there is some dependence of the transparency of the xenon on the way in which you freeze, the way in which you crystallize. So we are essentially borrowing a method from a group that used to be working at Fermilab. It's called the Bridgman method. It's used in a lot of crystal growth areas. You essentially set up a temperature gradient between the bottom and top of the detector, and you cool it down and you freeze from the bottom up. So the Fermilab group did this with a transparent glass inner cryostat and cooling through liquid nitrogen vapor, very exotic. In our setup, we do something that is essentially the same thing that you would do for a liquid xenon time projection chamber, these copper thermal links going to a metal cryostat. And we're able to essentially do the same thing that the Fermilab group is able to do. So we have these realistic scalable cryogenics. You can see here's a plot on the left that shows in blue our pressure as a function of time as we go through this crystallization procedure. So it starts off at time zero on the plot here, it's liquid, and we are cooling it over time. And suddenly the pressure drops to around the triple point, and that's when the crystal has finally reached the liquid at the top, and suddenly it brings the pressure down to that triple point. In addition, solid xenon is slightly more dense than liquid xenon, gives you a little bit of a bonus. If you use the same detector, you get a slight boost in your mass. More importantly, it contracts rather than expands, which means that you are much less likely to have to worry about breaking your PMTs when you're doing this crystallization procedure. Okay, so here's an actual event. It's just to demonstrate, look, it works. So we get each of these waveforms as a different SIPM channel. We see our initial signal, that's an S1, and our second signal, that's an S2. So we get the scintillation, we get the charge drift, we get the amplification in the vapor phase. So all of that works just like it would the liquid xenon version. So now let's make some quantitative comparisons. So we want to be able to prove that we can see at least very similar signals in crystal to in liquid. Our two signals, just to remind you, it's the scintillation S1 signal and the ionization S2 signal. So we have a cobalt-57 gamma source external to the detector. We compare it in crystal and liquid phase. As long as we're careful about the way we do this crystal growth procedure, we get essentially the exact same mean S1 size. We do the same thing with a polonium alpha, and we get, again, essentially the same S1 size. In this plot, the crystal S1 looks slightly bigger, but we'll be conservative and say it's the same. So it looks like our S1 signal is actually the same. The S2 signal, if the thing that makes it tricky is that we have this amplification phase. So what we really care about to some degree, if we're trying to quantify the particle detection properties, is what is the initial ionization yield. Doing that properly requires that you know exactly what your amplification is. And we're the setup at LBNL is still working on getting that exactly measured. But suffice it to say, we have seen no issues with seeing S2s in the crystal. And in fact, in this example here, our crystal S2s are, for the same field, are significantly larger than in the liquid. Part of that is likely to be due to the fact that the electron extraction efficiency from the condensed phase, either liquid or crystal, into the vapor is actually known to be higher when your condensed phase is solid rather than when it's liquid. So this is an old Russian measurement from the 80s that shows the extraction efficiency of electrons into the vapor as a function of electric field, and the crystal is higher than the liquid. And we haven't been able to measure those curves in our own setup yet, but we clearly see an enhancement in the crystal phase as well. In addition to the size of the S2 signal being roughly comparable, we see an actual improvement in the electron mobility. So the ability for electrons to move through the crystal at a given electric field is significantly higher in the crystal than in the liquid. This is again something that's been measured by groups prior to us. We see something like 1.6 to 2 times increase in electron speed in the crystal. A really nice way to demonstrate this is we have wires that form the cathode, the bottom electrode grid of our detector, that we coat with a little bit of polonium-210 and alpha decay. So that forms a nice peak at the maximum drift time of our detector. And we see that when we crystallize, the drift time of that peak shifts over to significantly shorter drift time in crystal. So this is actually relatively nice because that means in our detectors there's less pileup of events because the event window is shorter. And we also get fewer accidental coincidences of S1 and S2 signals. So this is actually a significant background for some large dark matter searches where you can get isolated S1s. They're created by spurious photon emission from various things. It could be coincidence of PMT dark counts. It could be light emission from electric grids. So those isolated S1s sometimes by chance get paired with isolated S2s caused by other things. And those conspire to appear to be a real signal when they're in fact uncorrelated. So by having a shorter drift time, you reduce the impact of those accidental coincidences. We can do the same procedure multiple times and we seem to get the same results. This shows the size of our cobalt peak as a function of time after crystallization and after some initial crystal relaxation that we're still studying. It seems like it's quite stable afterwards, quite stable and the same from one round to the next. Okay, now let's talk about radon decay in the crystal.
So before you go on, did you measure the diffusion too?
No, that will be something we want to measure in the future. Yeah. Okay, so I said crystal xenon removes the radon. So let me prove that to you. So this is a test where we take a radon 222 source, we continuously flow it past the condensed phase. So we've got the vapor going past the detector. Initially, the detector is in liquid, and as this flow is happening, we see the rate of alphas on the y-axis is increasing as the square root of time. So this is like a diffusive process. There's more radon buildup in the liquid as we have more radon coming through. We then cool down the detector, we freeze it, we continue to flow the radon past at the same flow rate. So that means actual flow speed has to go up a little bit as pressure goes down. And we see that after we've crystallized, we watch the rate of radon alpha decays over time. It decays away, consistent with no addition of new radon. It decays away with the half-life of the radon 222 itself. So just from this very nice and easy to digest plot, you see a reduction of at least a factor of 10 in the radon amount, essentially limited by the fact that this test took a month and we didn't want to wait another month for it to decay several more half-lives. So this test very nicely demonstrates a factor of 10 reduction, but we actually get much better than that. So we did another test where now instead of freezing the radon, the pre-existing relatively high radon rate into the crystal, now we wait until crystallizing to flow the radon. This case, we ended up using a different radon source because it had higher activity. That's what we needed to do. So we have, for the same exposure to radon, the same procedure. In the liquid, we get something like 2,000 alpha events. And in the crystal, we get 3. And those 3 events, we actually believe are not even from the radon that we flowed past, because they're not near the top where they would have most likely diffused from. They're in closer to the center of the detector. So we think this is actually, and this is consistent with the rate of radon 222 backgrounds before we started flowing the radon to begin with. So that suggests an exclusion factor of at least a factor of 600, maybe higher if these 3 alpha events on average are closer to 1 or 0. So already this is well above the amount of exclusion we need to make radon no longer a problem for these experiments. And we've significantly piggybacked beyond anything you can imagine doing with current technology for distillation. I mentioned the radon tagging idea. By chance, of our 3 events, we think that 2 of them were actually from the same decay chain. This shows the reconstructed position of events in the detector. The 3 alphas are shown as crosses. I know you probably can't see it very well, but there's an orange and a red that are right next to each other. They happen within a few minutes of each other, which is consistent with a half-life of polonium-218. So we think this is a radon-222 followed by a polonium-218 at the same location in the detector. And the shift in position is less than a millimeter, which implies that if we were to try to do this radon tagging approach in a real detector, what we care about is the half-life of the bismuth 214. That's the thing that comes right after the lead 214 that we don't like. We need to wait 20 minutes ballpark. That's the lifetime of that bismuth 214. And that would correspond to a shift of less than 1 centimeter. We can't quantify it exactly because we're limited by the position resolution here. But because that's comparable to the 1 centimeter is comparable to the position resolution of LV, essentially, these are going to be point-like events. You can have multiple decays in the chain across an hour or so time period that appear to have not moved at all. So you can, this is a good demonstration that you can do very efficient radon tagging. It's a suggestion. You can do very efficient radon tagging inside of the crystal. We'd want to do it with maybe more than 2 events to really, publish something. Okay, so we've demonstrated that we can do this at the very small scale. There's a big jump to go from 700 grams to 7,000 kilograms of LC. That's a factor of 10 to the 4. So I can't go to the DOE right now and say, here we go, it's going to work, fund us. We need to demonstrate something of an intermediate scale. So now that I've started my group at UT Austin as of January, we're actively working very hard to build up a demonstrator experiment at the 10 kilogram scale that will study these questions of scale up. In particular, we're interested in understanding how the crystallization time scales with mass. What are the effects of crystallization rate on the crystal transparency and other particle detection properties? So those are sort of the first most immediate goals of this experiment. The pictures on this slide essentially demonstrate me being excited about startup money and what you can buy with startup money. But we've got our outer vessel and our inner vessel, which you can't see. We've got our giant safety recovery vessels, our cryogenics, our fast digitizer for SIPM readout, some fancy new computers. My students had a great time designing. Okay, so looking forward, there are a number of things that we want to continue to study with this crystal xenon technology. Some using the small test setup at LBNL, and some using the larger setup that I'm building at UT. So first of all, we want to be able to quantify how well precisely can we discriminate between electron and nuclear recoils. And based off of our existing measurements, we think it's going to be very similar in liquid and crystal because the signal properties of the S1s and the S2s look pretty similar, but we want to quantify that exactly. So the LBNL group is hoping to do that this year. We also want to demonstrate that you can do it. If we're proposing to freeze LZ, we want to make sure that it's safe to freeze PMDs. So that's a small scale project that's going to be done. The UT setup, as I mentioned, is going to be focused on the scaling up of the crystallization procedure and how that affects the yields. We're also interested in how do we control the shape of the crystal vapor interface? The reason that's relevant is that the amplification in the vapor phase depends on how long the electrons travel through that vapor. So if you have a crystal surface that instead of being flat is concave, that will change your yield, and that's something that could be a complication. So we want to understand, are there ways that we can, as we're crystallizing, sort of adjust this to keep it flat? Are there ways that after we're done crystallizing, we can, maybe remelt a little bit of the top and do some fine tuning? We want to be able to have some feedback and control over this. Otherwise, it's probably going to be very hard to get the precision we need for this vapor phase amplification to be relatively uniform. As I alluded to before, high voltage is a real challenge for these very large xenon experiments. So we need to demonstrate that there aren't any extra high voltage challenges in the crystal xenon. And we want to be able to quantify the S2 response at the voltages that we can achieve. If this is really successful, then we could imagine going to a version where we actually do the amplification instead of through the vapor directly in the crystal. So we do charge amplification in the crystal. That requires higher electric fields that you usually get with smaller wires, basically field effects type enhancement. That's a wild idea, but if we can establish that that works, then we don't need to care about the vapor interface shape. Yes.
Yeah, just a point of clarification. So is it plan to have a segmented detector with several crystals, or just one big crystal?
Just one big crystal.
Okay.
Yeah. I mean, not a single crystal, but one vessel that's filled with solid zinc.
Okay, thanks.
Yeah. We're also interested in studying diffusion and the crystal. So we've already put some limits on radon diffusion with a small detector. We want to, if possible, try and either measure the radon diffusion constant in xenon or put a limit that says, okay, really, we don't need to care about this at all. Probably more interesting is electron diffusion in the crystal. To my knowledge, no one has measured this. And the reason this is particularly interesting is that electron diffusion is very relevant for neutrinoless double beta decay. And experiments like NEXO are xenon-based. They very much care about electron diffusion. So the two main benefits that I can think of right now for crystal xenon for neutrinoless double beta decay are, one, that again, the largest background to these experiments is radon. It's a slightly different flavor of radon. It's played out of daughters onto the cathode. But again, you remove the radon, you remove that background. It's not quite as dominant as it is in the dark matter detector version. So you don't suddenly get backgrounds swept down by a factor of 10, but it's significant. And in addition, if you have less diffusion of the electrons, that gives you better position resolution, particularly when you go to larger detectors where there's a longer drift time. And because of the way charge readout is done in experiments like NEXO, you're essentially measuring the charge signal over some time period. If there's less transverse diffusion along this axis, that means the time you need to measure the S2 signal over, the charge signal over is shorter. That means you integrate less electronic noise, so you get better resolution on your S2 signal. So you can, if there's less diffusion, you end up getting better position resolution and better energy resolution as well, both of which are very important when looking for neutrinoless double beta decay. The reason that I think it might be the case that electron diffusion is lower in crystal xenon is that what we care about is not comparing the electron diffusion constant. We care about the electron diffusion length over the period of the TPC. So if the electron diffusion constant is about the same, but it goes twice as fast, we're going to get a lot less diffusion. Yes.
Shouldn't the constant also depend on temperatures? And can't you make this arbitrarily cold essentially?
Yes, we are also going to study temperature dependence. There are challenges with going well below the triple point because the density continues to change. You continue to get contraction. So you'd need to think carefully about ways to sort of backfill the xenon gaps that you might get if you really go to deep temperatures. But yeah, you absolutely would want to study the temperature dependence, and maybe you could get a significant improvement that way. Yes.
I'm losing some intuition here because the gaseous xenon TPC folks also claiming they're having better energy resolution, and you're saying by solidifying the xenon you get better energy resolution.
They're sort of different types of effects. So this is energy resolution improvement potentially through removal of electronics noise. And the thought is that the recombination, the process that changes scintillation light, exchanges scintillation light and ionization, is maybe kind of the same in liquid and in crystal, whereas it's definitely not the same in liquid and in vapor, which is, I think, the explanation about the higher energy resolution in vapor. Okay, last crazy idea. We have just a couple minutes. So there's the suggestion of doping xenon with hydrogen. Specifically, what if you dope the LZ experiment after it's done running with hydrogen as a way of improving sensitivity to low mass dark matter. The basic idea is that now the hydrogen is the target for the dark matter coming in, and because it's got the hydrogen has a much lower mass, about 1 GeV instead of xenon's about 130 GeV, you get a much better kinematic coupling to the lower mass dark matter models. So you can take advantage of your very large size. You can dope with maybe 1% of hydrogen, and you can still get a very large, a very massive target of hydrogen, while still maintaining the benefit of the shielding that you get, removal of backgrounds from the xenon. And also, the key point, you are reusing an existing experiment, which would otherwise be very expensive to make. This also gives you increased dependence to so-called spin-dependent dark matter searches. So the proton has an uncoupled nuclear spin that if there's a dark matter model that couples to nuclear spin, you get increase and enhancement to that. So the challenge of hydrogen doping, though, is that the hydrogen tends to come out of the liquid into the vapor. The hydrogen really doesn't want to be in the liquid phase. Because the hydrogen is continually trying to come out, if you want to do this approach of hydrogen doping of liquid, you have to keep pushing hydrogen in. And there's also a very strong concern that the concentration of hydrogen in the vapor could quench your S2. So essentially you get this cascade of secondary electrons happening that's exciting xenon atoms in the vapor. But if you have 1% of hydrogen, maybe those hydrogen atoms they take some of the energy away from the excited xenon atoms and radiate it in an undetectable mode. So that's a real concern. We don't know if that's to what degree that concern is real or not, but crystal xenon solves both of those problems. So if you dope your liquid with hydrogen and then freeze it in, you don't have to worry about redoping, and you can also change your vapor phase to be pure xenon. You can wipe away the hydrogen and make it pure xenon. So that's a maximally interesting application of crystal xenon is combining it with this other kind of wild idea of hydrogen doping. So I'll stop there. Basically, we've already established that crystal xenon works really well as a particle detector. It works really well at excluding radon. We need to demonstrate that it's scalable to many kilograms to be useful for particle physics, but that's what we're working on right now. Thank you.
Does anyone have any questions?
Yeah, two quick questions that I think you mentioned and I missed. First, when you were comparing the like liquid versus the crystal measurements, did those both use SIPMs or did you use PMT for the liquid?
Yes, they're exactly the same detector. It's just it's this, and it's even exactly the same run. We liquefy, we do some measurements, and then we crystallize without opening up anything.
Okay. And then do you have a way like where you were measuring the transparency of the liquid versus the crystal?
Sort of indirectly. In the setup at UT, we're going to have a little camera. There you go. That proves that we'll have a camera. We're going to have a viewport that will let us look from above. That'll give us mostly information about the shape of the crystal, but maybe a little bit about transparency. We can have some LEDs at the bottom. But what we care most about is not transparency in the optical, but transparency in the UV, which is where the xenon signal is. So the best way to sort of observe that is by trying to measure the same signal with the same scintillation signal when it's passed through different amounts of crystal. And we kind of sort of did that in the previous setup, in that we have this polonium on the cathode wires, and we can see how much signal goes into the bottom SIPMs and how much goes into the top SIPMs. Directly, there is a light collection efficiency factor that you have to account for, but if we compare the ratio of the two in liquid to the ratio of the two in crystal, that light collection efficiency factor mostly cancels out. There may be some slight geometry changes, but and it looks like, in fact, there's no evidence of a loss of light when it has to travel not from here to here, but from here up to here. So we are pretty confident that if we're careful, we can get a highly transparent crystal, at least at this scale. If you need to make it 10, it would have to be about a little more than 10 times taller to be LZ scale. So more careful study is needed.
Impressive though.
Thanks.
So I guess I don't know all that much about how crystals work, but how are electrons able to drift through a crystal?
You can think of it as, so in a semiconductor, you can have a crystal, you apply the right voltage and the electrons move around in the valence band, fine. So the electrons in the crystal, you really don't want to think of them as being bound to a specific atom. They're kind of shared in the electron sea between the crystal as a whole.
So barium tagging is not on this list. Barium tagging is solid.
I personally am still a little nervous about suggesting the compounding wildness of crystal xenon at ton scale with the wildness of barium tagging. I also, for those who don't know, my PhD was doing barium tagging, and that particular approach didn't work, and it took a long time. So it's not the first on my list of things to explore, but it's definitely on the radar of people and the small group of people doing crystal xenon work.
Okay, because it somehow saves like Mike Mo's original idea, because, you know, now we know you can do it in solid.
Yes.
The thing's there in solid for free, right?
That's correct.
Layers are added and just get the photons out, right? What could be that?
What could be challenging about it? Yeah, no, I think it is a very exciting idea. Not something that I am personally going to be working on in the near future, but I don't know, maybe Shiloh will work on it.
Okay.
Yeah. Yes.
I'm just curious, can you freeze liquid argon instead of xenon?
You absolutely can. I haven't really thought about how this, what the benefits are in that case, how they translate between the two. Obviously, the radon exclusion is probably going to still be relevant. Argon is already much harder to liquefy. I don't know about much harder, but it's kind of close to the liquid nitrogen boiling point. I don't know if going from there to solid argon, that might actually pose an annoying cryogenics challenge if you're using liquid nitrogen for cooling. If you're using something else for cooling, it's probably fine. I'll think about it. It's an interesting idea. Yes.
Are any of the gammas from like the radon chain the problem? Like bismuth 214 emits a gamma sometimes.
So we live in kind of a different world than neutrinoless double beta decay typically. So the gammas from the radon chain are relatively high energy, and typically they're going to multiple scatter. So we can distinguish them from a single WIMP interaction pretty efficiently. So that, yes, they do contribute, but at a low enough level that no one is really concerned about it. In fact, if you get a beta decay that has a coincident gamma, you can use the gamma to exclude that event. The reason the lead-214 is particularly harmful is that there's a large fraction of the time that the decay goes directly to the ground state. So there's no corresponding gamma, and those are the ones that end up in the background. So really, when I say lead-214 background, I mean lead-214 ground state decay background.
Okay, any more questions? Okay, let's thank Scott again.
It's stable. Surprised at how it's